Today I want to continue talking about shared state, and I'm going to show you two things. One, a very nice idea called Tuple Spaces, and two, another concept called monitors, or synchronized objects. Tuple Spaces is a very interesting idea because it's in between shared state and message passing. So what does that mean? That's interesting because it lets you get a better idea of what shared state and message passing are. Let me first define it. It's a multi-set of tuples. I can make a picture. So a tuple space here is a multi-set of tuples, and you can put tuples in this multi-set, and you can remove tuples. Write and read. And it's a multi-set, so the same tuple you can put in multiple times. They're like tokens. They're like physical things. You put them in, you take them out, and you count how many there are. There are three operations. Write, so the TS is a tuple space. Write T will add a tuple to the tuple space. The read will wait until the tuple space has one tuple with label L. Notice there's two arguments here. Because a tuple can be a very complicated data structure, you can do some kind of pattern matching, that the read will wait for a certain kind of tuple, but here it's very simple. The read will wait until there's a tuple with label L. So L is an atom. And when there's a tuple with label L, it's removed and bound to T. Okay? And this will wait. So this is a concurrent operation. These are concurrent operations. The read is going to wait. So if there's no tuples in there, it'll just wait. And if somebody else, so another thread does a write, then the read will continue. So you notice a tuple space lets you coordinate between threads. Okay? And there's a variation of read, which is the non-blocking read. This one is if you don't want to wait. It returns immediately, and it has a third argument, B, which is a Boolean, and it tells you if B is false if the tuple space has no tuple with label L, otherwise it binds B equal to true. So this is similar to the read, except it does not wait. So this one is actually not used so much. You can use it sometimes if you want to do some kind of a management check whether something is there without changing anything, okay? But the actual computations are done with write and read. The tuple space idea was invented in 1985 by a computer scientist, David Galerter. He called it Linda. Maybe it was his girlfriend, I don't know. He called it Linda. And it uses pattern matching. That means when you did a read, it was like a case with patterns. Okay? So you can do that too if you want. Here the read will only wait for a tuple with label L. So that's very easy, right? In fact, there's really only these three operations, and the two are the most important. So it's a very easy thing, a tuple space. Sometimes the expression coordination model. If you read something and they talk about coordination model, they mean tuple space, okay? And a language that uses tuple spaces is called a coordination language. Why? Because it lets you coordinate between threads. One thread puts a tuple in and the other thread removes a tuple, okay? So this concept is actually used a lot today if you have what's called publish-subscribe systems. In a publish-subscribe system, it's like newspaper items. You can publish items, and then people can subscribe and read items. So the items are kind of like tuples, and the publishing is like a write, and the subscribing, you get notified whenever there's a message is like a read, okay? So these are actually coordination models. So it's used a lot today. So this concept is actually used a lot. It's a nice concept. Now, I want to compare this, so I'm going to show you some code for this, but I want to compare this to shared state and message passing. It's a funny concept because it's actually in between somehow. How can it be in between? Shared state, you have multiple threads accessing a cell, okay? And in message passing, you have a thread sending a message, and then a port object, which is another thread, will read the message. You have messages going. So how can this be halfway in between? Well, I'll explain it to you. The tuple space, first of all, it's shared between threads. Threads can do read and write. So it's much more than just one cell, huh? It's a much bigger thing, but it's also shared between threads. So it's a kind of shared state, a tuple space. But it's also kind of like message passing because the tuples are sent and received. A write is like a send, and a read is like a receive. And there's a very interesting difference with message passing. When I send a message to a port object, I know which one is going to receive it. Huh? I send it to that one. But here in a tuple space, the sender does not know the receiver. So you could have a sender, the write, and you could have many threads reading, and the sender sends, and one of these threads will take the tuple out, but the sender does not know which one. So it's like message passing, where the sender does not know the receiver. Okay? Because in regular message passing, you send, you know the receiver. Okay? But here, the sender, you put it in, it's like sending. But somebody will receive, but you don't know which thread. The sender does not know. And sometimes that's good. An example of that is like if you have printers. Let's say I have 5 printers, it's a big company, and the printers are reading from the tuple space. And the file I want to print is put in the tuple space, and one of the printers is going to read it and print. But I don't care which one, okay? It doesn't matter which printer actually prints it. As long as there's a printer that prints it, I'm happy. Okay? So that means you don't always need to know the receiver. So there's cases where it's okay to be anonymous. The receiver can be not known. So this is like message passing with anonymous receiver, but it's also shared between threads. The threads can be senders and receivers. So there's actually many senders and receivers. Also the receiver does not know the sender, but that's like regular message passing. In regular message passing, the receiver and the sender do not know each other. And in this one, in regular message passing, the sender knows the receiver, but the receiver does not know who sent. It could be anybody sending, okay? And here, it's anonymous in both directions. You might think, what about a case where the sender and the receiver both know each other? The sender knows the receiver and the receiver knows the sender. That's actually deterministic data flow. That's why it's deterministic, okay? So all possibilities are useful, in fact. Let me just make a little table of that. I have sender, the receiver. So the sender knows the receiver, and the receiver knows the sender. This is deterministic data flow. They both know each other. This is like a pipeline. In a pipeline, you have a connection, and it's deterministic, so the receiver knows exactly where the data is coming from. This is why it's deterministic. This is our very first paradigm. Now, if the sender knows the receiver, and the receiver does not know who sent it, this is regular message passing, what we saw with the port objects. And if neither of them know, then it's tuple spaces. Okay? So you can see actually it's a very nice way of categorizing things. The tuple spaces are very natural okay, in here. All three of these paradigms are useful. It turns out that this one is the one that people know most of the time. What airline is doing is the message passing. But the other two are kind of less used. Tuple Spaces has found a use now. In publish subscribe. It's actually found a use since the internet, but used to be not used. And deterministic data flow has also found a use now in big data analytics, big data tools in the cloud. These are almost always using deterministic data flow, and publish subscribe will always be using tuple spaces. So all three of these are actually useful, and you'll see all three of them, okay? Let me show you now some code for this. I hope you can read my writing there. The queue, remember the queue we did? We did it with locks last time. We also did it with exchange, the concurrent queue. I'm going to show you a third one now with tuple spaces. You can easily implement concurrent queue using tuple spaces, and you do not need a lock. You don't need a lock. The tuple space, it's very easy for the queue. So the way you implement a queue with a tuple space is the queue is actually stored inside. The data structure is stored inside the tuple space. And when you want to do an insert, you remove it, you do a computation, and you put the new state back in the tuple space. You read and you write. So you have to do one read, you remove it, you do the insert, and then you put it back in the tuple space. But you don't need a lock for that, because when you read it, you actually remove the tuple. So nobody else, if someone tries to do a delete, they will just wait, okay? So reading a tuple is like entering a critical section. When you read the tuple, you remove it from the tuple space, so it's not there anymore. And the first thread can do it, but once the first thread does it, the second thread cannot do anything because there's no more tuple, okay? So we've seen that three implementations. Last time we saw the queue with the lock, show how you do insert. So you actually have to create the lock, you enter the lock, you read and you write. But notice when you read a cell, it does not remove the value from the cell. It's not like a tuple space. The cell value is still in the cell, you're just looking at it. Whereas when you read from a tuple space, you actually remove it, okay? You can do also a queue with an exchange. That works because an exchange is read and write, and the queue only has to do one update. So that works because you have only one update. You can't always do it with exchange. When you do transactions, what we will see next time, then you do many operations and you cannot use exchange anymore. You still need lock again. But with the queue, you only do one update, so you can just use an exchange. Okay? And finally, the tuple space, you will do a read and a write, but you do not need a lock. Okay? So let me show you the code for this. So here's the new queue. I create a tuple space, and I have insert and delete. And the first thing I do here is I write an empty queue. Okay, so the queue is the same data structure as before. It's a tuple with three elements: the number, and then a difference list giving you the content. So 0 and then XX. So that's an empty queue. Then I return the queue which has insert and delete. Here are the insert and delete code. Okay, so the read here will read the tuple with label Q, and it will bind the tuple to this. So N will be the first, F and X bar B2 will be the rest of the difference list. And then it writes a new tuple with N plus 1. Okay, notice here I have actually bound the tail to X bar B2. So I've actually added X to the difference list. So F and the new tail, B2, is the new difference list. So that's the write. That will insert. And the delete is kind of the opposite. But it's also a read and a write. Huh? You read with label Q, and then I'm actually, this is the head of the Q, the first part of the difference list. So X is going to be bound to the first element, and F2 is the rest. So F2B is actually the rest of the Q, and X will be the output. Okay. And then I do a write with n-1 and with the rest. So that's the implementation using tuple space. Okay. And maybe I can very quickly run this code. Okay, so here I have the actual implementation of the tuple space, but let me go to the code here. So here is actually some examples, and then you can implement the queue. Okay. So let me compile this. In order to compile this, the tuple space, when I implement it, it actually has a queue already also inside it to implement it, okay? So it has actually, it needs that. So the tuple space here uses queue and dictionary to implement it, okay? And it also needs locks, but we use the system's locks for that. But I need this queue. Okay. That's good. And then I implement it. So it's implemented as a class here. Okay, that's good. It's accepted. And I'll just show you some examples. Maybe that's very simple. I create a new tuple space. So I run this. Okay. Now I can write a tuple. Here's a tuple with foo1. And here I can read the tuple with label foo. Okay, and you can see it here appearing. And here, for example, I can read a tuple with label bar, and I will show it here using a funny syntax. Let's see. Let me first let's put another two tuples called with label car5 and car6. But then if I read, let me not use this syntax, let me write it like this. Okay, so this will read a tuple with label bar, and then browse it. If I feed this line here, it will actually execute the line in its own thread. Huh? So here it will display nothing, because there's no tuple bar here. But if I add this tuple bar, it will display. Notice there's already two tuples with car. So I'm putting stuff in and taking stuff out. If I now add the tuple bar to, then this one, which is waiting in its own thread, will display, remove the tuple right away. Okay. That should remove it right away. Did I maybe not execute it? Oh, there. Yeah, I didn't execute it. So I can execute it again. And here, if I write this line, then this line, then this one will execute and it displays bar 2. Okay, let me just do that, okay? If you want to run the queue code, you can implement it and try it out, okay? So that's how tuple spaces work. You put things in, you take things out. Let me now just say a few words on how tuple spaces are implemented. This is actually interesting because it's using several data structures. This is the internal implementation of a tuple space. Notice it's using three things: a lock, a dictionary, and a concurrent queue. So to implement tuple spaces, we need a lock, okay? And it has a dictionary because of the patterns, the fact that we can wait for a tuple with a certain label, and it also needs a concurrent queue, because what if you put more than one tuple with the same label? Somehow you have to organize them, and they are put in a queue. So if you put 5 tuples with label bar, they will put in a queue, in a special queue, with all the tuples of the same label. Okay. So here we have a dictionary. A dictionary is like a hash table, so it's an indexed structure. You have a key, which is an atom here, and then you have some value. The values are going to be queues. Okay. So if I put in a tuple with label bar, then the key will be bar, and I will add a queue of tuples that have labeled bar. And if I put in a new label, foo, that does not exist anymore yet, the dictionary will add that. So it's a dynamic hash table. You can add new keys, and you can also remove keys. Okay. So if the queue is empty here, then you do not need this key, and it can be removed. So you can do kind of garbage collection for that. So the dictionary handles the pattern part of the tuple space, and the queue handles the part when you have multiple tuples with the same label. Okay. So the tuple operations, it will insert elements in these queues at the position of the label in the dictionary. Okay. And if the queue is empty, then you can actually garbage collect and remove this entry and save some memory there. You don't need to store empty queues because the dictionary is dynamic. You can add new entries and remove entries, and when you remove entries, the dictionary gets smaller. Okay. So most languages have this kind of a dictionary built in. In Oz, there's actually a dictionary module, so this is a standard data structure. Okay. So most languages like Java and so on, they have this kind of a dynamic hash table built in. Okay. Okay, so that's all I'm going to say about tuple spaces. If you want to know more, type coordination language, or you'll find a lot more on the internet. So I'm going to conclude now this is from last week's lecture. This is the introduction of shared state that we started. Remember, the number of interleavings is exponential, so the whole point is making big atomic actions. That's the whole idea. And doing that, we have locks, monitors, transactions. So far, we only talked about locks. Tuple spaces are another way of building big atomic actions, because a write of a tuple space is actually doing a lot of work. Okay? And a tuple space is a funny thing, because it's also kind of like a lock. When you remove the tuple, it's like token passing. Remember the token passing for the locks? Tuples are like tokens. When you remove them, then you have it and nobody else can have it. There's only one. If there's only one tuple with a certain label, it's like a token. Okay. So the tuple passing can also be like a lock. See, so it's actually a very interesting combination of message passing and shared state. And I showed that there's also 3 kinds of message passing, depending on whether the sender knows the receiver and the receiver knows the sender. Okay. So that makes 3 possibilities. Deterministic data flow, message passing, and tuple space. If you want to think about the 4th one, you can think about the 4th one. But I'm not going to talk about that here. So that's all I'm going to say about tuple spaces. And now we will go to monitors. Monitors, which are the devil's concurrency concept, the one I don't like, okay? But today I'm going to talk about monitors. Monitors, they're also called synchronized objects. A monitor is a lock with something more added, just like a transaction. It's a lock with something extra added. because locks are not good enough. In fact, they work for queues. A lock it was enough for a queue because you never have to wait. You could always insert elements. So the queue you can grow as much as it wants. In the queue I showed you, there's no limit. But in real data structures, it's not always like that. And the example is a bounded buffer. So again, we come to the bounded buffer, and I'm going to show you a shared state way of doing bounded buffer. But you cannot implement a bounded buffer with just a lock. So how would you do it? You put elements in, yeah, fine. You have a lock, and all the operations are inside the lock. Huh? You put elements in. But what happens if the buffer is full? And I try to put an element in. I cannot. I have to wait. But locks don't let you do that, okay? You go in, you go out. There's nothing that lets you wait in a lock, okay? Yeah, the lock just makes sure there's only one thread inside inside the critical section. That's all it does. But the actual data structure does not wait, okay? Or what happens if, so the buffer is full, the lock cannot do it. What happens if the buffer is empty and you do a get? If you do a get, you try to get an element, but the buffer is empty. You have to wait until another thread does a put, okay? You have to wait. So that means the locks are not good enough. And if I have one thread doing puts and another thread doing gets, then the thread doing puts has to wait if the buffer is full, and the thread doing gets has to wait if the buffer is empty. And you cannot do that with just locks. It cannot work, because locks do not have this waiting operation. Okay. So this shows you that locks are not good enough for real concurrent data structures. Monitors were invented to solve this problem. And they're very old, so they were invented by a computer scientist called Per Brink Hansen in '72, and Tony Hoare, who was another famous computer scientist. He actually was one of the people inventing also message passing in 1974. So they're very old things, almost 50 years old, and they are widely used today. Okay, still used a lot, but I don't like them, and I don't want you to use them. But I'm going to explain how they work. Okay. So you see why locks are not enough, huh? So let's see how you extend the locks. The monitor adds two operations and a data structure called the wait set to the lock. So you have a lock plus that. The wait set is actually a set of suspended threads. The monitor lets you suspend threads. When they try to use the monitor, they might suspend, okay? And wait and notify are how the threads talk to each other. Notice the wait and notify operations, you only do them when you're inside the lock, never outside. They're part of the lock, and you should only do them inside the lock. Huh? The intuition is following the wait. When a thread calls wait, it is suspended and is put in the wait set. So it forces the thread to wait. Okay? And it's put in the wait set, and then you leave the lock. The lock is released, so the lock is available for another thread. Okay? So the thread is in the wait set, and it's waiting, and it could wait forever, okay? And a notify operation, a thread can call notify, it will wake up the thread in the wait set. It will resume it, let it start executing again. This woken up thread will do what all threads try. It will try to get the lock again, at the place where it was suspended. So it wakes up exactly at the place where you did the wait. And it tries to continue. So basically it's like the wait operation continues. Okay? So that's the intuition. But now let me be more precise. I'm going to give a more precise semantics This is exactly the Java semantics. It's a simple semantics, and it's popular, and it works pretty well. So I'm going to give you this Java semantics. So this is how it works in Java. Some languages have little bit variations, but mostly it's like this, okay? So in Java, a monitor is an object, okay? In Java, it's object-oriented, and you extend it with a lock and a wait set. So this is called a synchronized objects, and there are 3 operations: wait, notify, and a third one called notify all, okay? Of course, you have to execute them inside the lock, inside the critical section, never outside, otherwise it's buggy, okay? And here is the semantics. The wait does this. It suspends the current thread, so stops executing, and that's a message to the scheduler. Right? Don't choose this one. It places the thread in the wait set, and it releases the lock. That's very simple, huh? The thread just stops, and so the wait set is storing the thread, and the lock is released. So some other thread can get the lock, okay? The notify operation is the following. If the wait set is non-empty, then it does something. If the wait set is empty, the notify does nothing, okay? But if the wait set is not empty, I will remove an arbitrary thread. I just pick one, and I resume it. That means it starts executing again at the point it was suspended, okay? At the point it did a call to wait. And that thread will do what any thread does when it tries to, when it's inside a lock. The wait makes it release the lock, but when you resume it, it tries, because it's inside the critical section, the wait, it tries to get the lock again. It tries to get the lock again. Notice it cannot, of course, immediately, because the thread that's doing the notify is still in there, okay? So the T that is resumed tries to get the lock again, but of course it will not immediately be able to do it until the notifying thread leaves, okay? So usually the notify is done at the end, the critical section, and the notifying thread will then go away, and then the woken up thread will succeed in getting the lock, okay? If it's the only one. Maybe there's more threads trying to get the lock, okay? So it will get the lock whenever it gets the lock. Maybe there's another thread also trying to get the lock, and then of course, it depends on how the lock chooses the thread. But if it's the only one, it will get the lock as soon as the notifying thread leaves the critical section, okay? That is the wait and notify, originally. It turns out notify is actually not so nice. So real systems, they will add another operation called notify all. Okay? So notify will resume an arbitrary thread in the wait set. But what if you have multiple threads? What if I have a bounded buffer and I do many puts and they're all waiting? Okay? And then I do a get. How does the notify know which one to resume? Okay? So the notify picks an arbitrary thread. But sometimes this is a problem, as we will see. So in real monitors, applications, almost never use notify. It's weird, huh? We define this notify operation, and I'm telling you not to use it, okay? But you use another one called notify all. Notify all actually wakes up all the threads in the wait set. Maybe there's 100 threads trying to do put. They all wake up and they all try to get the lock, okay? That's a mess, but it works, okay? All threads are resumed. All threads try to get the lock. The wait set is completely empty after you do notify all, okay? In real monitor applications, it's almost always notify all. So wait and notify all. Okay. So this all seems very theoretical, but I'm going to show you code now that does this, okay? And you will see how it works. Okay? So one of those many threads that were woken up will get the lock and will execute inside the critical section, the monitor. If somehow it's the wrong one, then it will wait again. If it's the right one, it will do whatever it has to do. Maybe you're implementing a tuple space and you're putting in many tuples of many labels, and you only want certain label or something. If it's the wrong label, it goes back to sleep, okay? Notice if you have many threads woken up, this gives a situation called contention. So contention happens when you have many threads trying to do the same thing, which is trying to get the lock. It's perfectly fine. It's not a bug. It's just something that gives overhead. If maybe there's 100 threads woken up, okay, and only one of them is the one you really need. Well, the 99 other threads will all be woken up and will all go back to sleep again. That's kind of overhead, but that's how it works. That's how monitors work. And the one thread that does the right thing, it will actually do the right thing, okay? So contention is a problem sometimes with monitors if they're highly loaded. Okay, so all of that is the theory. Now I'm going to show you the code of an application, and I'm going to return to our good friends, the bounded buffer. Remember, we already saw one in lazy deterministic data flow. But here we're going to do a bounded buffer in shared state. So in lazy deterministic data flow, only one thread puts and only one thread removes. It's a pipeline. But here, anybody can add, put, many threads can put, and many threads can read, can get, okay? So it's a more general, non-deterministic version. I'm going to then now explain again what is a bounded buffer. So let's say here I have a bounded buffer of size 10. So I have an array of 10 elements, and I have two operations. A put operation and a get operation. Put operation will put something, like here it's a data G in the bounded buffer, and the get will remove the one that was put longest ago. So here the get will bind X to A and the put will put G. And the maximum size is 10 here. Okay, so the put and the get operation, we're going to define it using locks and monitors. The specification is here with 3 operations. So buffer is going to be a class. I create a new buffer B of size n. So a new buffer init n. And then there's 2 messages I can send, 2 methods. Put X, put element X in the buffer. If the buffer is full, wait until there's room. So the thread doing the put will wait if the buffer is full. And get, remove an element from the buffer and bind it to X. If the buffer is empty, then the thread doing the get will wait until there's at least one element. Okay, so you notice that the 2 thread, any thread can do put, any thread can do get, but if it's full or empty, there's going to be waits going on. Okay, you see that, huh? So this is a typical kind of thing where you need a monitor to implement this. Okay. To implement the bounded buffer, I'm going to organize the array as a ring. And the reason is that when you reach the edge of the array and you keep putting and you remove elements, you actually are moving around to the other side. So the easiest way to implement a bounded buffer is to organize the array as a ring. So here we have the array 0, 1, 2, 3 up to n minus 1. And we have 2 pointers in this ring. A first pointer and a last pointer. Okay. When I do a get, I use first. So a get will get A, and then it will increment the the first pointer to point to B. So I remove A, B, C, okay? And the last is for adding elements. If I add an element, I put it here, and then I increment the last. So you see, the whole thing is going to be going round and around, in a sense, huh? I remove elements, this one is going to be moving like this, I add elements, it's going to be moving. So the two pointers are going to be going around and around, and once they go past n minus 1, it starts with 0 again, okay? If an index is outside interval 0 and minus 1, it's replaced by index modulo n. So you're always on the ring, okay? Notice you can have two operations that block it. If the buffer is empty, then first and last will be the same, okay? So the number of elements is actually last minus first, okay? Last minus first. And if the number of elements is 0, then last and first are going to be pointing to the same element. And if you try to get, you have to block. Okay? Also, if last goes all the way around and is pointing here, just next to first, then the number of elements will be actually be n, then you have to block also. And when you try to, if the last is here and you try to add an element, then you also have to block. So there's two ways that you have to block. Okay? So that's how the bounded buffer implements. Okay? You see the idea. This is a very standard data structure. Okay? So here is the code of the bounded buffer, but I'm not using the monitors yet. Okay? So I define a class with a buffer attribute, which is an array, the first, the last, the size, and an index. Okay? And I have the init. I'm going to use an Oz operation called new array. I'm not going to explain so much. So this creates an array that you can access using dots. Like you can do array dot something to access the array. Okay, so it's kind of standard. I'm not going to explain very much. It starts by first and last being equal to 0. Okay. N is the number of elements in the buffer, and I is actually the size. It's how many elements are in there. Okay. So here's how it works. So the put will put the element at the last position. Notice you have to use the read symbol always for accessing. Huh? So the array buff dot last colon equal x. Okay. And then I increment last. Last is last plus 1 modulo n. And also I increment the size. I will be the size. Because sometimes it's nice to know the size. Huh? We'll see. So that's how it works. But notice you have to do a wait. Okay. There's no pointer here. But here, you cannot always do this. Huh? You have to wait until I is less than n. So that's the ... code. And I'm not telling you how it works here. Huh? That code is going to be done by the monitor. Okay? So all of this has to be done inside the lock. Eh? Notice I'm doing multiple assignments here. Right? This is an assignment, this is an assignment, this is an assignment. There's 3 assignments. So these are all cells actually, yeah? These attributes. So all of these have to be inside the lock. Huh? So far I'm not showing you the lock. And the get is doing just the opposite. So it waits until I is greater than 0. So there's at least one element. And x, which is the output, will be equal to buff.first. I increment first, mod n, of course, and I decrement I. Okay? So that's how it works. But now we have to add the monitor. Okay? All of these are in the lock, and somehow we have to do the wait. So I'm going to show you how to use wait and notify them to do this. Okay? So you see the code, right? This is standard kind of code, and it's easy to translate in Java if you want to translate this in Java. And I'm going to use a monitor abstraction. I'm going to use the full code. Monitors are not a default abstraction in Oz. I actually have to define them separately. And so I will define them like this to add the monitor. I will define a function called new monitor. The new monitor M is actually a record with 4 fields. It has lock, wait, notify all fields. Lock is a procedure. They're all procedures. Lock M, wait M, notify all M are all procedures. And then these are the way to use them. The lock is like we saw before. You introduce any statement here, but it's higher order. So the statement is turned into a 0 argument procedure, and this is a re-entry block, like we saw last time. And wait, notify, all are just called like this. Wait, notify, they're 0 argument procedures. Okay? So that's pretty straightforward, okay? Standard kind of thing, and most languages are going to be do it kind of standard way, okay? So with this, we can turn the bounded buffer, which I showed here, into a complete piece of correct code. Okay? So here is the code for it. I'm just going to add the red pieces, and then we'll make a break and I'll explain how it works. So here I have, I'm creating a monitor, M. I have another attribute, a monitor. So synchronized objects in Java, they automatically have that. Here, so this is the code, is now inside a lock. Lock, it's m.lock procedure end. All of this is inside the lock. And the red part is actually the wait. If I is greater than or equal to n, then I wait. And after I wake up, I have to try again. So I actually call put again, okay? And since it's a reentrant, there's not a problem. If I is less than n, then I take the else, then I actually execute the code, and at the very end, I do a notify all. So this is very standard. I'm always doing wait in the beginning and notify all at the end. Okay? So that's the typical way to use a monitor. But this code is actually more subtle. It's kind of subtle because it's concurrent. So what I will do now is I make a break so that you can already start meditating on this. And then I explain how it really works after the break. This code is right, but to explain why it's right, let me show you a buggy version, which is this one. And I want to ask you now why it's buggy. Here I have a put, okay. I again have a lock. If the buffer is full, I is greater than or equal to n, then wait. Okay, and then when it's not full, then the wait continues. It adds the element, and then it does notify all. This seems reasonable, right? But this one is buggy. So I want you to see if you can figure out why this one is buggy. It looks reasonable, right? If the buffer is full, so this is a good comparison, then I call wait. And someone else that does a get, okay, the get will remove an element and do notify all, okay? And the get will work, because since the buffer is not empty, the get can remove an element. The get code will do notify all, and then the put that did await will resume, and it will start executing. And since there's a slot available, it will add an element, and it will seem to work, right? So if this put is done when the buffer is full, and then I do a get after that, The get will remove an element, the get will do notify all, the put will wake up, and it will succeed because there's a slot available, right? So that's correct. That's one scenario. But there are other scenarios with this code that actually make it go wrong. So this is actually a buggy program that will be totally incorrect, okay? So what do you think? Maybe I give a hint. I give you a hint. Let's say I do 2 puts, okay, and then a get. What happens then? If I do a put now, and the buffer is full, so the buffer is full, I do a put, it's full, and I wait. Fine. And then I do another put. Well, the buffer is still full, and I wait. So now I have 2 threads in the wait set that are trying to do puts. Okay? Reasonable, right? And now I do a get. And the get does notify all. Both of the waiting threads are woken up. They both try to get the lock, but only one can actually get the lock. Okay? That one does the put, right? And then what happens? Then what happens? You have to think concurrently. So this is something I've been telling you in the course. You have to imagine that what happens in weird cases, okay? If you really want to think concurrently. So I do 2 puts, they're both waiting, okay? You get that? And then I do a get, and the get will do a notify all. So both of the waiting puts are woken up. They will both try to get the lock, right? But of course only one will get the lock. The other one will wait at the entrance of the lock. And the one that gets the lock does this, and does notify all. But the wait set is now empty, so the notify all does nothing. What happens after that? What happens after that? The 2 are both woken up. The 2 try to do put. One of them gets the lock and goes here. What happens to the second one? Yeah?
Il est libéré du lock et il continue sans wait qu'il y ait des éléments.
Libéré. Donc le deuxième, the second one. Et ça donne quoi? Continue ton histoire qui commence bien là. Ton histoire commence bien. You start well.
Il va essayer de rajouter un élément alors qu'il y en a déjà trop.
So the get will wake up both threads, and they both try to get the lock. One of them gets the lock. Okay, the other one is still waiting at the entrance of the lock. The one that gets the lock will do a put successfully because there's a slot, and then leave. What happens to the second one?
Il essaie de aussi mettre un élément.
Il essaie aussi de rentrer, et ça donne quoi? Il réussit?
Ouais.
Oui, et ça donne quoi quand il réussit? So the second thread, trying to do a put, will, as soon as the first one, which successfully doesn't put leaves, the second one was waiting, will then successfully enter the lock, and what happens then?
Ouais, il met un élément dans un buffer qui est déjà prêt.
Oui, he tries to put an element in a buffer that's already full. Boom. Well, that means he's going to overwrite. It's going to be wrong, of course. You can't put an element. What happens then? Well, then you increment last, even though the buffer is already full. Actually, that means the last will actually be equal to first. So it's like the buffer's empty. But I will be incremented. So it's totally weird. It's completely buggy. Okay? So this doesn't work. When you wake up both threads, they're both waiting for the lock. But when you do a get, only one slot has been created. So only one is actually allowed to do a put. The other one should go back to sleep again. So how do you do that? So what's the, so this is wrong, huh? So it seems weird, huh? Wait and notify are tricky things, okay? So how do you get this to work correctly? There's actually a very simple way. It means before you do this, you have to check again whether there's a slot. So you have two threads doing a put. When one of them, when the get happens, then before they actually put it in, they have to check again the condition. Il faut retester si le buffer est plein. So the first one that's woken up will see that there is a slot, but the second one will see there's nothing and go back to sleep. Okay? So in fact, you have to test again after you wake up. So this should not be an if, it should actually be a while loop. Because after you wake up from the wait, before you do the code, you have to test again, because maybe there's no slot. Maybe the second put, some other put went ahead in the scenario, and so the slot disappeared. So it's not because you wake up that you're guaranteed to have a slot. Okay, so that's buggy. So the right way to do it, so in Oz you have to do it like this. So here you have the wait, and when you wake up in this wait, you're not allowed to do this right away. You have to test again. The way you do it in Oz, you have to actually do a recursive call to put. So you actually try again to do a put. So you completely try again to do a put. Okay? You try again. And in the scenario, let's say you have two threads doing put. Okay? And the get wakes both of them up. Both of these threads will try to do a put again. We'll completely execute this code again, and the first one will see that there is a slot, and will do it, and the second one, it's not time yet, the second one will see that the buffer is full, and will go back to sleep again. Okay, so the way to make it work is after you wake up from the wait, you have to check again whether there is a slot. And you have to do the check inside the lock. Okay? In this code here, in this buggy code, when you wake both of them up, both of them are outside the lock. One of them goes in and does a put. The other one is still outside. So they have to go in again. Once you get in, the only way to guarantee that there's a slot is to check it when you're inside. Okay? So the way to check that is here. You have to again check. So the check is this condition. So after you wake up from the wait, so you have two threads waking up here. Both of them have to check. And if there's only one get, then only one of them will actually be able to do the put. The other one will go back to sleep again. Okay? Of course, you can magnify this scenario. Let's say I have 100 threads, 100 trying to do a put on a full buffer. They all go to sleep. Okay, fine. Then I do one get. Notify all of the threads wake up. And they all try to get the lock. The first one will successfully do the put, and then when it leaves the critical section, the others will also get in there. So they will all be able to do the put, so the thing is totally broken. Okay? Okay, in this code though, this is the correct code, what happens? Let's say I have 100 threads trying to do a put on a full buffer. They will all go to sleep. They will all be in the wait set. 100 sleeping threads. And then I do one get. Okay, what happens? All of the sleeping threads are woken up. 100 threads are woken up here. And they will all try to do put again. And the first one, the lucky one, who's first, will actually see the slot. I is less than n, will do the put. And then the second one will see that it's full and go to sleep again. And all the 99 threads that come after the first one, they will all see the buffer is full and they go to sleep again. You see, it's kind of overhead, huh? If I have 100 threads trying to do put, and I do one get, then it will wake up 100 threads, one thread will do the put successfully, and the other 99 will go back to sleep again. That's a lot of work, huh? Of course, this is very rare. It depends on a situation where you have 100 waiting puts. Usually you don't have that. Okay? So the rule is that before doing the operation, you have to do a check again. Because maybe somebody else already took the slot. Okay? Like in the example with the 2. So this is the pattern. There's actually a general pattern for monitors. When you use monitors, unless you are very smart, you must always use this pattern, okay, if you want it to be correct. This is the bounded buffer. This is using a while loop, okay? In Oz, there's no while loops, so you use recursion. So recursion is the same as a while loop, huh? So this would be how you would do it in Java, for example. With a while loop, you have a lock, while not full. So expression would be if there's a slot available. While there's no slot available, I wait. But when the waiting thread wakes up, it's still inside the while loop. Okay? It wakes up, and the first thing it does is it goes back to the while loop and checks the condition again inside the lock. So we'll only execute the statement when there's a slot available. Okay? And the other threads that wake up will automatically do a wait again and go back to sleep. Okay? So the wait has to be inside a while loop to be correct. And the notify all is just done at the end. Okay? So when you use monitors, you always have to use this programming pattern. It's a very simple pattern. And if you want to do anything different, there are thick books on concurrent programming in Java. There's a famous book by Doug Leah called Concurrent Programming in Java. It's like 300 pages. It shows you lots of things. Some of them are very subtle, but the basic idea is always the same. When you wake up from a wait, you have to check the condition again. So it has to be a while loop. Okay? In Oz here, it's slightly different because Oz does not have while loops. It's supposed to be mostly functional. It's weird. It could have them, but doesn't. Okay? Maybe I should add while loops. So in Oz, you have to do it like this. You have to do recursive call. If not expression, then recursive call. Self again to this one. So this is exactly the same as a while loop because this one will test the condition again. So remember we saw that tail recursive function is the same as while loop. So these two are actually exactly the same. But it's a little bit shorter if you have while loops when you write the code. Okay? So if somebody forces you to write code with monitors, which I don't recommend, but maybe you are forced, someone points a gun to your head and says you must use monitors, then do it like this. Okay? So that's how it works. I'm going to show you now some code for this. The next thing I'm going to show you now is how monitors are implemented. And this is a little bit more complicated than reentrant locks. So essentially we're going to build on top of the reentrant locks. But before doing that, let me show you just an example of this code. Okay? Of making it work. Okay, this one is the monitor. So this is the monitor implementation. So monitor uses a queue internally.
I'm not going to explain it right away. This is the monitor implementation, okay? So let me first compile it. This is a queue. The wait set is actually implemented as a queue. This is the monitor procedure. Notice internally it uses cells. So I implement this. Okay, this is good. And now I'm going to show you an example. The bounded buffer example. So I'm not going to show you the buggy one. So the buggy one is here. So this code I will put on the Moodle. So here's the correct version of the bounded buffer. Here's the put. So lock. And so this is all inside the lock. Wait until the buffer is not full. So if the buffer is full, I is equal to n, then I wait. And after, when the thread wakes up, I try again. I do a put self. Otherwise, if the buffer is not full, then I can put the element immediately, and at the end I can notify all. Okay? And I'll show you the code for get also, because I didn't show you the get before, but it's completely symmetrical. Okay? I have lock procedure n. Now, if the buffer is empty, so I is the size, then I wait, and then when it's woken up, I have to do recursive, because the condition might become false again, because maybe multiple threads are trying to do gets. And if it's I is different from 0, then I can do the get immediately, and then I do notify all. Okay? So that's the bounded buffer, a correct version. And if you want to write it in Java, it's very similar, it's just a different syntax. Okay. So here's some code that uses the buffer. So BB is a bounded buffer of size 3. I can put A in the buffer. I can get an element and browse it. And now I can put elements in the buffer and do things. Okay, so for example, I create the buffer here. Size 3. I put A in the buffer. I display. So let me show you the... Here. So here you see the A coming out. If I now try to do another get, nothing will be displayed. So let me do another get now. Thing. So nothing. So there's a thread now waiting on a get. If I now do another put A, then the thread doing the get will show the A. You can see here the A. I can put, so now the buffer is empty. If I try to put 3 elements, okay, let me execute this in one thread. I put 3 elements, A, B, C, and then I try to put D, the 4th element. I browse this so they can see what's happening, and end 4th, when it successfully puts in the 4th element. So it will succeed putting in A, B, C, but the 4th element will block. Huh? So here you can see, try 4th. So it all executes up to here, but this one is blocking. Huh? And if I want to put in a 4th element, I have to do a get. Okay. So here I do a get, for example, and I remove A, and then the 4th element is in. So now the buffer has B, C, D. Okay. And so you can experiment with, see how the bounded buffer works. Okay. I'm going to show how the bounded buffer is implemented. This is extending the reentrant locks, okay? Monitors are extension of reentrant locks. There are 2 changes we have to make. Of course, we have to add the wait set. We need something that's the wait set. So we're going to use a queue to implement the wait set. The wait set, it could be a set, but a queue is nice because that means it ensures a kind of fairness. If I have multiple threads in the queue, then they all move. When I remove threads, I'm removing them one by one.
It ensures fairness. It's not possible for a thread to stay forever in the queue. So a stack, it would be wrong, huh? If we, instead of a queue, would use a stack, then maybe the guy in the bottom of the stack is never going to be chosen. I put elements in the queue, I remove, and if I never remove everything, the guy in the bottom is starving. Okay? So a queue is better than a stack. This is why when you go into a store, people are waiting in line in a queue and not in a stack. Huh? When you wait in line in a queue, you are guaranteed to progress and make it to the front. Okay? If you wait in a stack, then the first person, if I have a stack of people, then if more people come into the store, they get served first. The guy at the bottom of the stack will wait the whole day, will never get served, okay? So stack is not fair. You don't need, if you want to do a waiting, you don't use stack. So we're going to use a queue, okay? That's the first thing. The second thing, we are going to slightly modify the reentrant block. It's not a big modification. I call it get release lock. So the entering and the leaving are actually separate. In the regular reentrant block, we actually have it together. You enter, you do the body, and you leave. They were together. But now we actually have to do them separately because we need to do them in different places. Entering and exiting the critical section are separate operations called get the lock and release the lock. But otherwise it's the same as a regular reentrant block. Okay? And the queue also has a few extra operations. We have a delete all operation because for implementing notify all. Notify all will take all of the threads out of the wait set. So we have to somehow take all of the elements out of the queue, so we're going to add a delete all operation. Okay? So here's the get release lock. Okay? So now we have two operations. Get is to get in the critical section, and release is to get out. Okay? Get is the hardest one. It does like this. Okay, first of all, it's reentrant. So again, we check the identity. Okay, if the identity is different, then we actually have to do something. Again, we do an exchange. We have token passing and wait. Okay, now we have to be careful because the release maybe is done later on, and the release has to bind this new one to give the token to the next thread, okay? So we don't actually know when the release is going to be done. So the release has to bind this variable. So what we do is we put this variable in a cell called token 2, and then the release actually can bind new. So this passes the token, huh? So we need this token 2 because the release and the get might be in different pieces, running in different pieces of code. So this is slightly different. Instead of, we can't just use new here, okay? Because we don't know new. New is created locally inside here. Huh? We don't know the new here, so we can't use new. We have to do something else. We can do it using token 2, okay? And we can't make new global variable because you can run get and release multiple times. Each time you do a get, you get a new variable. Huh? You get always new variables, okay? So you have to put them in a cell, okay? So basically that's it. Otherwise it's the same code as reentrant blocks. But we've split it then into a get and release, okay? And it returns here the two things. Notice the get is actually a Boolean function. This is kind of interesting, which tells me if it actually had to do some work. So if the identity is different and it actually has to wait for the token, it returns true. But if I'm already in, it returns false. And this is important because if I'm already in, I don't have to do release later. I only have to do release if I did this, okay? If I'm already in, then going out, I don't have to do anything. So to make the distinction, this get lock is going to be a Boolean function returning true or false, depending on whether it actually did work for getting in or not, okay? So that's the get release lock. You see, it's a little bit more complicated than the regular reentrant. And now we have the queue. This is basically the same queue as before. Okay, it has a cell internally. It has a lock internally. It has its own lock internally. Okay, fine. It doesn't. You can also use declarative queue, but here I'm going to show you one where it has its own lock internally. Fine. Okay, and it has a cell internally. So insert and delete are the same. I add a new function called size. I had a new function called delete all, and a new function called delete non-blocking delete. Okay. The delete all it creates a lock here first. It gets the difference list SE, and it binds E to nil, and then S will be a list of all the threads that are waiting, okay? So it returns all the waiting threads as a list, okay? The delete non-blocking here, this one will return one element in a list if there's an element or otherwise return nil, okay? So you see how this works? And now I can show you the code for the actual monitor, okay? This is the new monitor function, returning the record with the 4 procedures. And now we can see how each of these is implemented. So the lock M, this is a regular lock. It's like a regular reentrant lock. And the way we do it is, it's actually very similar. If you look at the code of get and release, you'll see it's the same code as before. But we can implement using get release. If get, then, so if it's true that when we actually did work to get the token, we do try P finally, and we do release at the end to release the token to the next one. Otherwise, if LGet returns false, that means we're already in the lock, and then we can just execute P because it's reentrant. Okay? So you see the get and release are used in a regular way, just like a regular reentrant lock. So if you look at the code, this is actually the same code as the regular reentrant lock before. But now we have these extra functions, wait, notify, and notify all. First of all, the wait has to suspend a thread and put it in a delete, put it in the wait set. So how do you put a thread in the wait set? It's not really data structure of thread. So the way we do that is we use a data flow variable, a single assignment data flow variable. To suspend the thread, we do wait x. So the wait operation will suspend until x is bound. If we do a wait x inside the thread, that will suspend the thread. And we will put x, this unbound variable, inside the queue. Okay? And later on, when we do notify, we just have to bind the x, and then it will cause this waiting thread to suspend again. Okay? So here's how it works. The wait m, after I explain this. So I create a new unbound variable, x, I put it in the queue. Q is a queue, this is a new queue that I created, insert x. And then I release the lock, semantics of the wait. Notice this is using the get release. I know I'm in the lock here. The wait is executed inside. So I know I'm inside, and so I release here the lock. Okay? And so I'm totally out of the lock. And then I do wait x. Here I'm outside of the lock. But when the thread resumes, I have to try to get the lock again. So I will do a get. Okay. But here I know I'm completely out. So I know the get will always return true. Okay. So I do, because I'm totally out, it will get the token.
So it will always return true, so I do if, get, then skip, end. So the if is just to ignore that true, because I know I'm always out. So you see how the wait is working? It's exactly the semantics, huh? It puts it in the queue, it releases the lock to stay suspended, and when the thread continues, it tries to get the lock again, at the same place in the code, where the wait is called, okay? And if you look at the notify, notify is removing one element from the queue. So this is the delete non-block I've implemented. So there's two possibilities. Either the queue is empty or it's not empty. If it's not empty, then I will have an element here, x, and I will bind x to unit, which is a constant. So this causes the waiting thread to continue, okay? This causes the wait to continue again. So this is what wakes up the thread, okay? And the notify all is very similar, except I use delete all. L is a list of unbound variables. For x and L, I do x as unit. This wakes up all of the threads, okay? All of them are woken up. Since they're all waiting here, and they will all wake up. So you see how it works? It's not so complicated, right? But it's a subtle program. And I can prove it was subtle because the first edition of the book, the code was buggy. There was a bug in here, okay? Terrible, huh? And so, but the current printing has fixed the bug. So you can see that even we made a mistake when we made the first code. But as far as I can tell, this is correct code, okay? If you can find a bug in here, I will pay you a beer, no problem. No? So I think there's no more bugs in here, okay? Okay, so that's the implementation of monitors. So you can see how it works. Huh? Notice it has both a lock and a queue inside here, and the queue has its own lock itself, okay? The queue has its own lock itself, fine. But the implementation that I show you here is actually slightly different. The one I will put in the Moodle. So the one I put in the Moodle, this actually, you see it's a slightly different one. It's the declarative one. Okay? You see it's the completely declarative one. It doesn't need a lock or a cell. And if you look at the actual monitor code, it's slightly different. Not much, just a little bit. Let me show it to you. So for example, the weight, it's here. Notice it's slightly different because the queue is a declarative data structure. So when I do an insert, it returns the new value of the queue. So queue is actually a cell here containing the state of the queue. So I do insert queue X, and this is the new queue, okay? Then I release the lock, I wait X, and then I do get lock, and then skip. So this is the wait. You see the only difference is that this is a declarative queue. The insert is now a declarative operation. And so queue here is a cell. Huh? So you see it's just a little variation. Huh? The queue is going to be a cell. Okay? So that's how it works. See that? So I really encourage you to try out this code. To try running it. To see, so you really understand how it works. Okay, so let me go now conclude on monitors. Monitors are extending locks, okay? You can suspend and resume threads depending on conditions. You have a wait set, and you have wait and notify operations, where we're adding and removing a set and a thread in the wait set, and you have notify all, okay? The reason why you have notify all and not notify is because you use, if you have only one wait set for a monitor, the threads might be waiting on different things. If you have puts, they're waiting for a get. If you have gets, they're waiting on put.
One of them is waiting for the buffer to be not empty, the other one is not full. And in big monitors, it can be waiting on multiple things. And if you only wake up one thread, you might wake up a thread that's waiting on the wrong thing, okay? So you have to do notify all, but some languages have variation where they have multiple wait sets in the monitor, more complicated, okay? And each wait set is waiting on one condition. So that's kind of complicated. So Java does not do that, and most languages don't, but sometimes they do that, okay? So monitors are actually very hard to program. Wait and notify are difficult. So the way to do that is to use a programming pattern. The pattern is guaranteed to be correct. Okay? So I showed you the pattern. And again, I say it's widely used in legacy, but I don't recommend you writing the code. Okay? So that's where we end today. The next week, we're going to talk about transactions. Transactions is another way of extending locks, and they extend it with the ability to abort. That means you can return and the state is not changed. It's still atomica. So monitors also are atomica. So when you leave the lock in a transaction, either you did something or you did nothing. So you have commit or abort. And this is very important for databases. All the large databases are using transactions. So whenever you do something on internet, you are doing dozens or hundreds of transactions without knowing it, okay? If you buy something on Amazon, you are doing dozens of transactions in simple operations. So that we'll see next week. Okay, so let me stop here. I think that's all. I don't want to say any more today. We're a little bit early, but I think that's fine, huh? I've actually showed you a complicated thing. So I expect you to understand how this pattern works. Huh? And if I give you a buggy version of a bounded buffer, you should be able to explain exactly why it's buggy. Huh? Okay? I'm warning you. Huh? This could be exam question. Huh? There. Okay. Simple.